All right, so part 3 of solving trig equations, and this we're going to look at 2 cosine squared x minus 3 cosine x equals 2. And our domain for this problem, or where our answers are all going to come from, is between negative pi and pi. Okay, so let's discuss that right out of the blocks, just so we know what we're looking at. From negative pi, the angle negative pi starts with this initial side there and goes there to negative pi. And then positive pi starts on the positive direction and goes to there. So our answers, we're looking for answers in all 4 quadrants, but we have to be careful how we get there. We can't get to the 3rd quadrant and 4th quadrant angles by going in a positive direction. We have to go in a negative direction to get to those angles. So it's likely we'll have some negative angles as our answer in this problem. All right, now this is different, right? What's different about this problem than anything we've looked at so far? Last problem had a tangent squared.
There's 2 different length things.
I have cosine squared and I have cosine. Right, so we're going to need to do something to do this. Now let's look at an algebra. Your instincts are good. Let's look at an algebra equivalent of this. Let's look at what we would do if we had, let me change variables here. What would we do if we had 2a squared minus 3a equals 2? How would we solve that algebraic equation? We would set it equal to 0. What tells you to set it equal to 0? The square, right? Spence, you can't factor out the a because we don't have a 2 product rule, but we do have a 0 product rule. So we can set things equal to 0 and factor it, and when we factor it, so the technique would be to subtract 2 from both sides here, and that would give us that equals 0. And then we would factor that as 2a and a minus 2 plus 1, right, equals 0. And then we would set each of those factors equal to 0, and we get a equals negative 1/2 or a equals positive 2. Right? So that's just a quadratic technique that's going to come into play. And we're going to use that quadratic technique, even though we're not dealing with the polynomial function, it's still going to apply with our trig functions. So I'm going to subtract 2. Anytime you have squares, and really often in trig equations, if you have multiple trig functions, like here we have the cosine squared of x and the cosine of x, that's 2, it's the same trig function, but those are 2 different representations of the cosine of x. So we're going to subtract 2 and make it equal 0. And then we're going to factor this exactly the way we just factored that algebraic expression. So the only option for 2 cosine squared of x is going to be 2 cosine x times cosine x. And I have negative 3 cosine x that I have to get from 2 times negative 2 is negative 4. So I'll need negative 4 and positive 1, right, for my factors. So to get to negative 4 cosine x, I put the negative 2 over here, and then positive 1 from there. Then that does give me 1 times negative 2 is negative 2. So that's the correct factorization of that trig expression.
Are you recording this?
I am.
Okay.
Would you like to say something to the recording?
No, that's good.
You know, some
Maybe
YouTube
later.
jargon?
Oh, okay. Like, comment, subscribe.
Okay, thank you. All right, so then when we set each of these factors equal to 0, Spence, here we can set the factors equal to 0 because the 0 product rule says the only way you can multiply and get a 0 is if you're multiplying by a 0. So either 2 cosine x plus 1 is equal to 0, or cosine x minus 2 is equal to 0. No, we got to solve it because remember our ultimate goal is to find this angle x. We want to know what these angles are, right? What is the value of this angle? So here cosine x would have to equal negative 1/2, and here cosine x would have to equal 2. Ooh, danger, right? Can cosine of x equal 2?
Negative goes right.
It cannot. So we are not going to get any answers from that one. No solutions can come from that. Then that's similar, if you'll remember back into algebra, when we were solving rational equations, sometimes we would get a solution that couldn't be a solution. We had to kick it out. It doesn't make sense because it would give you a 0 on the denominator, or in this case, invalid. There's no way cosine of x can be 2 because cosine lives between -1 and +1. Okay, so the solutions that we're looking for here come from where cosine x equals -1/2. And it's going to be in all 4 quadrants. Where is the cosine equal to -1/2? Quadrant 2 and quadrant 3? Okay. So I got to have one of my answers here, quadrant 2, and one of my answers in quadrant 3. Okay. So what's the reference angle for cosine x is 1/2? My reference angle is pi/3. And I'm going to put that in quadrant 2 and in quadrant 3. And this will be 2 pi/3, correct? Here. And remember, I cannot get to this one by going around here because we're restricted to the positive angles to pi and the negative angles to -pi. So I have to get to this angle by going here. So that is going to be -2 pi/3. All right, so my two solutions are going to be 2 pi/3 and -2 pi/3.
I like those kind of range problems.
Yeah, where your domain is kind of different. It makes you think about it. Well, it's okay. It is a range where our answers are going to be, but not specifically range in the sense of we're dealing with x values for our variable here. But we're not talking about functions, so we don't strictly have a domain and range, but I'm trying to be a little technically correct and use domain. But the interval where our answers must be are from -pi to +pi. So that kind of forces us to think that way, right? Okay? Is everybody good with that? So if there's a square involved, we're going to use quadratic techniques. So let's take a we're gonna do some more similar to this, but let's take a time out and go back and look at some of the previous examples that we've looked at, just to kind of do a review of what we've looked at so far, the techniques that we've been involved with. So I don't want to go all the way back to part 1 because those problems were really pretty simple. But part 2 started right here. So let's just look at it in that form. And again, what did we do there? We had to make a substitution for sine of 2x. Why did we make that substitution? What has to be the same? The angles, right? This is, remember, if we're taking the sine of something, that something has to be an angle. So we had to do something to make the angles the same. And that was doing that. And in Spence, this is where we subtracted cosine x. We still set it equal to 0. We still employed a quadratic technique there, factoring and using the 0 product property. Okay, and then, go ahead. Did you have a question?
We used a property.
We used the 0 product property. And we used a trig identity. Sine of 2x equals 2 sine x cosine x.
Yeah, we used an identity.
Yeah, we used an identity. So to get the angles the same. All right, and then the next problem, the next example we looked at was, let's see, I'm having a hard time seeing it, it's so small. Was the last one we did, the tangent x. And this we used, again, we used a quadratic technique. If we have something squared equals a number, then we get the squared part by itself, and then we use the square root property and got tangent of x equals plus or minus the square root of 3. And then the last example we worked was a full-blown factoring problem where we had to factor it just like we would a ax squared plus bx plus c equals 0 scenario. So these trig equation techniques, really the easy ones just resemble two-step inequalities. Not two-step inequalities, but two-step equations where 2x plus 1 equals 0. And so x equals negative 1/2. And then the more complicated ones, though, are going to start looking more like the quadratic techniques that we used before. Okay, so let's work with, let's see what's next. This one. Tangent of x equals negative 2 sine x for all x in the real numbers. So this is where we have every x involved. So we're going to have 2k pi's or 2 pi's or k pi's or involved here in our answers. Which in some instances are easier because we don't have to worry about which direction we're going to get to that reference angle. We just put it in a quadrant, name it, and add 2k pi to it. Okay? K is an integer. We'll define that when we give our answer. Now, what's different about this one? It has tangent and sine. Any ideas what we should do here? What do your instincts tell you to do after our trig identity section? Write tangent in terms of sine and cosine, and that's a really good thing to do. Sine x over cosine x equals negative 2 sine x. Okay, now what?
Bring the negative 2, like the negative 2 sine x, instead of equal to z.
Well, is nothing squared?
That's not what I would do. You could do that, but I think there's a better way. I want to show you the best way on this one.
Wait, is negative 2 sine x, is that equal to something? Like is that
No, we don't have an identity for that.
Okay,
I mean, I'm sure it's equal to something, but nothing is going to help us. Here's what I want us to do. Cross multiply. Because, if we can do something to get rid of that cosine x, that's going to help us, the denominator of that fraction. I do want to, because you mentioned it, I want to kind of show you what would happen if you bring it over, because you can do that. Then we would have cross multiplication would give us sine x equals negative 2 sine x cosine x. Now that's an identity, but we don't want to use that identity and make that sine of 2x because that would make the angles different. So here we're going to go back to the technique we've been using and make this 0 because I can see something that can be factored out, right? 2 sine x cosine x. Actually, I need to change the original problem. 2 tangent x. Go all the way up to the top and add a 2. Yeah, it's not that big a deal.
What does that do?
Just add 2 everywhere.
Just trust me.
Why doesn't that change the cosine?
Yeah.
Oh, because that's tangent x. And then the 2, it's 2 over 1. So, yeah, I apologize for changing that. But this is not, it's not going to have a nice solution if we don't do it that way. I must have copied that problem down incorrectly. So I can factor out a 2 sine x. That's correct. And I can factor 2 sine x out, and I'm left with 1 plus cosine x equals 0. Okay, any questions about how we've gotten to here?
No.
Okay, so let's take 2 sine x equals 0. or 1 plus cosine x equals 0 because of the zero product property. We have to remember that x is any angle in the real numbers. So I need to finish solving over here. I would get sine x equals 0 for this. And here I get cosine x equals -1. Okay, now using your special angles or your table of values or your unit circle, what angles x have a sine value of 0? 0 and pi, and then 2 pi, 3 pi, 4 pi, 5 pi, 6 pi. So think about that. That's 0 pi, 2 pi, 3 pi, 4 pi, 5 pi. That's all the pi's, right? So we could just write this as k pi, where k is any integer. Because 0 is an integer, right? 1 is an integer, 2 is an integer. And then we go in negative directions, negative pi, negative 2 pi, negative 3 pi. All those are solutions as well. So we don't have to use both of these. Of course, we could have said that x equals 0 plus 2k pi, and x equals pi plus 2k pi. And that gets all of them as well. But this more concise answer is the one that you're going to see most likely in a textbook.
But, like, I put 0 plus 2k pi and pi plus 2k pi.
Yeah, that's
Would you
okay
accept
also.
that?
I would accept that answer because it's correct.
If we,
Yeah.
on our exam, if it's multiple choice, it won't have, like, both. So which one might be, like,
Yeah.
box?
I'm not likely to
Do some of them?
ask this in a multiple choice scenario, not these all real angles ones. But if I did, you know, you'd be able to figure it out. If you're not seeing 2k pi's there, if you're just seeing k pi's, then you'd have to get your answer to match the correct one. Rachel?
Could you explain the 0 and pi, x equals 0 comma pi? Like, how'd you get that?
Yeah, look at your unit circle. Or look at your table of values, right? Where's the sine equal to 0? You're looking at the unit circle. Where's the sine equal to 0? Remember, the coordinates of your points on the unit circle are cosine comma sine. So 0 and pi.
Yeah. Okay. So you don't use cosine at all?
Well, I haven't finished. These are the solutions from this
Oh,
inequality.
that's just for sine?
Yeah, I still have to do cosine of x equals -1. But while you've got your unit circle handy, tell me what angle has a cosine value of -1.
Pi?
Pi. But guess what? Listen now. Pi is correct, but pi is also right there. So I don't need to relist that answer.
So those are your only answers. The K
That's
pi
it.
and
Mhm.
Can you explain the k pi, k-e-z, whatever? I don't know what that is. I don't think
K
I
is
ever heard
the
that.
element of
All right. If we were going to list these answers individually, we couldn't. Right? You can't list them individually because it continues from 0. We just keep going all the way around back to 0, all the way around back to 0. And you have to consider every angle every time it touches that. So that's 0. And then the pi was also a solution. So pi is over here to the left. Pi is a solution. So there's a solution, there's a solution. There's a solution, there's a solution. So the names of those angles are 0, pi, 2 pi, 3 pi, 4 pi. But we have to also consider that we can get to those angles in a negative direction. So we could go this direction and get to pi, and that's negative pi. So the negative answers would be negative pi, negative 2 pi, negative 3 pi, negative 4 pi forever, right? So a shortcut way of saying that is it's every k pi where k is any integer. What are the integers? 0, 1, 2, 3, 4, 5, 6, 7, 8, negative 1, negative 2, negative 3, negative 4, negative 5, negative 6. So the integers are these values right here, 0, 1, 2, 3, 4, negative 1, negative 2, negative 3, negative 4, forever in both directions. So we just do a shorthand way of saying that's k pi where k is any integer. And that's always a difficult concept for students to grasp in this solving trig equations section. Okay, let's go to the next one. Next example. I think this next one's going to be the last one, and then we're going to practice. Now, what we're going to do today is I'm going to give you a homework assignment from the textbook, and then we'll also have a look at tomorrow. Miss Dye is going to be meeting with you guys in class, and she'll be pulling you out one at a time for a couple of minutes each to discuss, I guess, graduation scholarship stuff. Anyway, she's going to be doing that tomorrow during this class period and fifth period. So tomorrow during this class period we'll go over homework and we will practice more. We need to start talking about when we're going to test on this. Maybe Friday. But I haven't looked at the test calendar yet. Okay.
What about Tuesday?
Tomorrow?
No, I meant
Next Tuesday?
So we can have Monday to like.
All right.
have a little review.
So here's another example. 2 sine squared x minus sine of 2x equals 0. 2 sine squared of x minus the sine of 2x equals 0.
Did you really think I meant tomorrow?
Yes, I did. Would you want it? No, that's not that good.
Now we've got a problem here, don't we?
We don't have a number.
But it's already set to 0, so we don't do the
Oh,
thing.
you're right.
We can factor
We take it a
out.
Sine X.
Yeah.
We can't take out a sine x because I have sine squared x and I have sine of 2x. So the problem here is what's the problem that I'm having here?
It's not the same angle.
I have different angles and I can't have different angles. Houston, we have a problem. So I can't solve an trig equation with different angles. So I have to use an identity to make the substitution here. So what is the sine of 2x equal to?
2
Sine
Sine
X cosine X.
2 sine x cosine x.
And then you can.
Now I can take out a sine x because I have a sine x in both of these terms. Prior to making that substitution, I did not have the ability to do that. Yeah, I can take out a 2 sine x actually. So 2 sine x, not s sine x, 2 sine x times sine x minus cosine x equals 0. And we didn't discuss this yet, but we're going to go one revolution in positive direction. So 0 to 2 pi. All right, so we have 2 sine x equals 0. Or sine x minus cosine x equals 0. And this is going to take us back to something that we did. I can't remember when we discussed this, but this second little equation there is going to be a little more challenging. Here we have sine x equals 0. That's easy. We just did that one, right? Where is the sine of x equal to 0? 0 and pi. I could go to 2 pi, but this is strictly less than 2 pi, so I can't go all the way back to 2 pi and get the next one. Now the next one is a little bit tricky. Sine x minus cosine x equals 0 means that the sine x has to equal the cosine x. From your table of values or from the unit circle, which angle meets this description? Where is the sine of x equal to the cosine of x? Pi over 4 in which quadrants? Pi over 4 in quadrant 1,
In quadrant 3.
quadrant 3. They're both negative in quadrant 3. They're both positive in quadrant 1. Okay, so pi over 4 in quadrant 1 is just pi over 4. Pi over 4 in quadrant 3, that's 4 pi over 4, so this would be 5 pi over 4. So my 4 solutions here are 0, pi, pi over 4, and 5 pi over 4. Okay,
0, pi.
Claire? Quadrant 3, the cosine and the sine both have the same value. In quadrant 3, they're both negative square root of 2 over 2. So cosine is equal to sine in quadrant 3, and cosine is equal to sine in quadrant 1. In quadrant 2 and quadrant 4, and this is going to come into play in your homework assignment, cosine and sine have opposite signs. So if you were to come up with a solution here that said sine x equals the opposite of the cosine x, sine equals negative cosine x, that's quadrant 2 and quadrant 4. Okay, so you kind of have to be mindful of this one. This one is a little bit more challenging because it doesn't give us a numeric value. It forces us to know where the sine of x is equal to the cosine of x. And if you look at your unit circle, that's quadrant 1 and quadrant 3. All right? Y'all okay with that? All right, let's, who has a homework sheet I can look at?
I do.
There's one handy. Well, let's talk about homework for this section.
There's one printed out though, and I don't remember which one it is.
So our homework for this will be section, in 5.1 or 5.3?
I think it's 5-3.
Section 5.3. We've already done up through problem 20. Now, we've not paid a whole lot of attention to anything in class related to using calculators for this, but I want you to give these a shot. The first two right out of the blocks might play with you a little bit, but we'll clean it up tomorrow. Section 5.3, 21 and 23. You're going to have to use your calculators for those. And then I want you to do...
Wait, why do I have to use my calculators?
to find because they won't be exact values. Like 21 is tangent of theta equals negative 15 over 4. So you'll have to do inverse tangent of negative 15 over 4 to find out what the angle is and then put it in the correct quadrant. Again, 21 and 23 will be a little tricky. 21 and 23, and I also want you to do 27 through 30. And 33 is going to challenge you. But let's stop right there. Okay?
Right.